This video is to explain the first problem, not from the book, on the worksheet that you received on Moodle Wednesday or Thursday, depending on when I saw you. So in this problem, we have a 3.6 kilogram block sliding down an incline. So the very first thing I want to do is to get a diagram going. So if I have an incline, that means that if this is the horizontal, I have a 17-degree angle, and I have an object sitting on that of mass m. Well, they tell us that the mass is 3.6 kilograms, and you can put that 3.6 inside. I just made my diagram a little bit too small to do that. So we also know that it is sliding down the incline, and we want to find the acceleration of the block. So the block is going to go down the incline, so acceleration is in that direction. Now, acceleration is not a force, so I'm not going to draw it on my free body diagram, but I might make a kind of separate arrow to show that I'm trying to find that acceleration on down that incline. So if you remember, acceleration is related to the net force in whatever direction it's moving. So in order to find my acceleration down the incline, I need to find my, so usually I use arrows to indicate well, what I know, but I won't use an arrow since that might confuse you. I need to find the net force also along that incline. So in order to get the net force down that incline, I need to figure out what forces are going on and put them together. So I have the force due to gravity, and even though it may be tempting to draw it like this, gravity always acts straight down on an object. We also have a normal force since it's sitting on a surface, and if you remember, normal means perpendicular, so it's going to be perpendicular to this surface. So it's not going to be straight up and down like when we have a flat surface. Perpendicular to this would be at a 90-degree angle, so imagine making an L there, and it's going to come upwards on that angle. That's going to be my normal force. Now normally we would also have friction force acting this way. I'll kind of put a dotted line because we'll do a friction problem in a little bit. But I would have a friction force that way, opposite of the motion, but we're ignoring that for today. So really all we have is gravity and normal force. Now part A, I told you to find the force due to gravity. Well, force is related, the equation for force we know from Newton's second law is force equals mass times acceleration. Now you may be confused in saying, well, I thought we were trying to find acceleration. Well, the acceleration we're trying to find is the overall acceleration of the object, which is related to net force. When we're finding the force due to gravity, we need to know the acceleration due to gravity. We do know that. That's always going to be negative 9.81 meters per second squared. So to find the force due to gravity, just take the mass, 3.6, and multiply that by the 9.81 meters per second squared. So that force is going to be, if you take out your calculators and follow along, 35.316. But because this has two significant figures, we're just going to say that that's negative 35 newtons. Well, up here, if you notice the arrow is already pointing down, that takes care of the negative. So the magnitude is 35 newtons. The direction is down. And so now we have something to work off of. Part B, I asked you to find the normal force. Now this is where things start to get tricky. In order to find the normal force, you need to pay attention to the fact that the normal force and the gravity force are not directly opposite. So the normal force will not be 35 newtons. In order to find the normal force, we need to break up our gravity force into vectors, into the vector components. To do that, if you notice, eventually we're going to have this friction force. If you notice, friction force is along the motion of travel, normal force is perpendicular. So instead of doing our xy axis like this is normally what we're used to, we're going to rotate this a little bit, rotate it this way, so that now our x-axis is going to be along the plane of motion, and our y-axis is going to align with the normal force. So I'm going to now tilt my axes to go with my incline. So now, here's my x-axis, here's my y-axis. I'm going to draw my vectors with the tail at the origin as they appear in my diagram. So gravity goes straight down, so it's going to continue to go straight down. And actually, if you give me a moment to, I can just do this. I want to do this in different colors. So here's my gravity force going straight down. On this axis, I'm still going to go straight down. And I know that that was 35 newtons. Now, my normal force, if you notice, is going straight perpendicular to the surface. And we said that the surface is our x-axis here. X, X. The normal surface is perpendicular. Well, perpendicular to the x is our y. So I'm going to draw my normal force here. So now, if you notice, the normal force is perfectly on the y-axis. The gravity force is not. In order to break this up into components, we need to know the angle with which it's making with the x or the y-axis. And if you really want to understand why this is, I can explain it to you at another point in time. And I did explain it in class. But whatever your incline angle is, that angle will always be made between your gravity vector and the negative y-axis. So it will always be on this part, not with the x. So I'm going to write in real small here, 17 degrees. So now we need to try to make a right triangle here. And you can really tilt your paper if you want to, so that you're looking at the x-axis normally and your y-axis normally. And I've actually done that with my computer, even though you can't see me do that. So here's the straight side, and I guess they're both straight, but what I mean by that is here's going to be your leg. The gravity vector is going to be your hypotenuse. So we need to drop the perpendicular this way to get our right triangle. So here's our right triangle. Now, if you look at this very carefully, this side, you have to ask yourself, is that the x or the y component? Well, it's parallel to the x-axis, so this side is going to be FGX, and that's a vector, so it's going that way. When I look at the other side, right here, this side, since it's going along the y-axis, is going to be FGY. So now, if we want to find both of those, and since I have the same color, I'm just going to go with FGY. That side is adjacent, it's next to the 17-degree angle. So I'm not going to use sine for y like we've been accustomed to. Use your triangle. It's the adjacent side, so we're going to use cosine. So FGY will be 35 cosine of 17. And FGX since it is the opposite side, will be 35 sine of 17. So using your calculator, and remember we're going to have two significant figures for both of those. 35 sine of 17 is 10 newtons. I guess technically we have to write that. The only way to get that with two significant figures is 1.0 times 10 to the first newtons. So I'm just going to write that in parentheses. You can work with 10 though. This one, 35 cosine of 17, is 33 newtons. Now technically FGY, if you notice, FGY is going down. So just like this was negative, this is going to be negative. And our FGX is going in the positive x direction, so that 10 newtons can stay positive. So now, we need to think about a couple of things. We're looking for the normal force. Normal force is right here. What other vector is in the y direction besides normal force? So hopefully you've kind of paused and thought about that. Normal force is here. If you look along the y-axis, normal force and FGY are together. And so really, what we have going on, if you notice, our block is not going to be moving at all in that direction. Our block is not accelerating into the ramp. That doesn't really make any sense. Nor is it flying off of the ramp. And so our acceleration is 0. That means our net force is 0. This is equilibrium. So because of equilibrium, we know that our normal force plus our gravitational force in the y direction must add up to 0. So that means that since they're opposite directions, they have to be the same value. Our normal force plus negative 33 has to be 0. So our normal force is going to be 33 newtons. And that's the final answer for part B. Now for part C, just before we jump to C, the reason why this is because there's equilibrium in the y direction. This will always stay with us, really. The normal force will always be the gravitational force in the y direction. So now, if we move on, part C asks the acceleration down the ramp. So the ramp, if you notice, is the x direction. What forces are acting in the x direction? Well, if we look at it, we have normal force in the y, gravity in the y, gravity in the x. The only thing happening in the x direction is FGX. So really, F net in the x direction is the same thing as FGX. So that means in our equation, net force equals mass times acceleration. We can take that 10 newtons that we had, set it equal to mass 3.6 times acceleration, and now it's a one-step equation. Divide both sides by 3.6. And remember that 10, even though it looks like it has one sig, it really has 2. So we have 10 divided by 3.6, and that is 2.778. So rounding to two significant figures, this would be 2.8 meters per second squared. So our block is accelerating 2.8 meters per second squared, which means that every second is getting 2.8 meters per second faster. So after 1 second, it would be going 2.8 meters per second. After 2 seconds, it would be going 5.6, and so on.